Following on from the previous video, I was saying how you can truncate a series. So let's say you've got a series like this. You can truncate it right here. So everything here becomes your Taylor polynomial. And then here you've got your remainder, you've got a remainder, you've got another block of remainder, another block of remainder. You will have more remainders over here all the way to infinity. You will have more remainders over here. But the clever part of this Taylor formula is that is how you're able to squeeze all these remainders into one simple, elegant block. So you've got lots of remainders here. The clever part is in being able to squeeze all these remainders into one simple, elegant block. At this stage here, you don't understand how it's possible that you're able to squeeze all these into one block. I'm just asking you to accept it for the time being. But the clever part is in being able to squeeze all these blocks into one simple block. So in this video, we're going to try and understand why it is that that when you start out with your Taylor polynomial. So let's say you start out with your Taylor's polynomial. So you've got a constant here, and then you add another term, and then you add another term. And what we're going to try and understand why it is that when you keep on adding all these terms, eventually this whole thing here will eventually becomes your true function. We're going to try and understand that why it is that if you keep on adding all these terms, eventually the whole thing here becomes your function. We're going to try and understand why. And the key to that is understanding that as n heads towards infinity, meaning if you keep on adding all these terms all the way to infinity, if you add up all these terms all the way to infinity, this thing here will head towards zero, because this thing here represents your remainder. It represents all your remainders. So if you can show that this thing here heads towards zero, then your Taylor polynomial becomes your true function. So the trick is to show that that as n heads towards infinity, this block here, the remainder, tends to zero, and then you can see that this thing here heads. This thing here becomes your function. So let me just quickly scan through the explanation, and then maybe in the next video I will give you an example. So hang on. So the trick to understanding why this works is to try and show that this thing here heads towards zero as n heads towards infinity. So as n heads towards infinity, it means that you keep on adding these terms all the way to infinity. So if you keep on doing that, we need to show that this thing here heads towards zero. So let's rewrite this. Let's take this out and then move this up here. So let's rewrite this as this. So let's rewrite this as this. So move this block out here. So that becomes this, and then push this into the fraction. So it becomes this. Now we've seen. Remember, our aim is to show that this thing here heads towards zero as n tends to infinity. So we've seen this before. Whenever you see something like this, something to the power, I know it's n plus 1, but let's just simplify it and consider n. Well, whenever you see this, something to the power of n and then n factorial. So whenever you see this, try and visualize this. So here you've got n, you've got 5, you've got a constant, you've got a number that when you power it by n times, so it's really 5 times 5 times 5 times 5, and then remember n is moving towards infinity, so n would be a very, very big number. So if you look at this here, here you can see that the numerator is bigger than the denominator, but then as n heads towards infinity, meaning this n here is very, very big. Let's take it to 1000, say. So here you can see that everything here will be much, much bigger than the numerator here. So you can see that this thing here will head towards zero as n heads towards infinity. So whenever you see this, consider a constant to the power of n, and then this n here is going to be very, very big factorial. So eventually, well, whenever you see something like this, the denominator here would be much, much bigger than the numerator. So this whole thing here will head towards 1 as n heads towards infinity. So whenever you see this, try and visualize this in your mind. You can see that, okay, this bit here, the numerator will be bigger than the denominator. But eventually, as n heads towards infinity, the denominator here will be much, 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 much bigger than the numerator. The point is that this thing here will head towards 0. And then if you look at this here, this thing here, let's just say you start out with a function sine of x. If you keep on differentiating it, the n plus 1 derivative will always be in between 1 and -1. So this block here is C is somewhere in between -1 and 1. Sorry, hang on. Sorry, I'll take that back. This block here will always be the whole block itself. The whole block itself will always be in between -1 and 1. So this block here will always be in between -1 and 1. And this thing here is heading towards 0 as n heads towards infinity. So you can see that the remainder heads towards 0, meaning that this thing here will eventually become your function. I didn't explain this very well, but hopefully when I give you some examples, you can see why that's the case. Okay, so this is what I've been trying to explain all along. Okay.